Welcome to Smart Chocolate, a show about ZK products where we break them down with rich flavors and sweet insights. My name is Omer, and I'll be co-hosting this episode together with Queenie. Today, we are thrilled to be joined by Yisan and Jonathan Wang, co-founders of Axiom, to talk about OpenVM. Guys, it's a pleasure to have you here. Could you please introduce yourself and provide some background on your company?
Hey, thanks for having us on. So my name's Yi. I'm one of the founders of Axiom. Prior to Axiom, I was a professor at U Chicago, and we've been building ZK infrastructure with Axiom for about the last 2 years now.
Thanks a lot for having us. My name is Jonathan, also co-founder of Axiom. And prior to this, was in math research doing number theory. For the past 2 years, working across different parts of ZK, primarily focusing on circuits and how to provide good interfaces for circuits and a little bit on the proof system.
All right, great. Let's start with asking the obvious question. What is OpenVM?
Yeah, so OpenVM is a new approach to ZK virtual machine construction, which is a framework for building modular and extensible ZK virtual machines. So the fundamental belief behind OpenVM is that developers will need customization to create ZK virtual machines for their individual use case and achieve the best performance. And so we wanted to build a generic framework which can allow developers to tailor ZK to their needs without compromising on performance. To give a sense of what OpenVM can do, we have a concept of virtual machine extension through which all features in OpenVM are implemented. And we support extensions for RISC-V, as well as common operations in elliptic curve cryptography, hashing, and proof recursion.
So it's great that you clarified the positioning of OpenVM, because when it came out, I think many people just took it as another ZKVM. So it's actually a framework, as you just mentioned. So I'm curious, can we compare OpenVM to LLVM in terms of functionality, but considering that OpenVM operates in the context of ZK?
Yeah, I would say philosophically, we took a lot from the approach of LLVM with the idea that different components in the system should be modules that developers are free to mix and match to build their own pretty powerful systems. Obviously, LLVM is a pretty high target to live up to, but we hope to continue adding pieces to the system and get there in terms of functionality.
And one thing I think is interesting with the ZKVMs is in like traditional LLVM, they are kind of limited at some point by the fact that like they can't control the actual hardware and like what processor this is actually going to be run on. But with ZKVMs, like because you're also emulating like the full machine architecture, you actually get to also do modularization at this like this level that's usually you have to just leave it to like a foundry to create something.
What is the current status of the project? Also, what is the roadmap? What are the next steps? How close are we to become production ready? Or maybe it already is.
Yeah, so we just had the initial release of OpenVM v0.1 in December, right before the end of the year. And we're currently actively developing to get to a production release in the next couple months. To give a sense of what's already supported in the framework, through the RISC-V pathway, we're able to prove the execution of mainnet Ethereum blocks. We also support proving arbitrary length programs through a Rust toolchain. That involves some continuation support, with which we have on-chain EVM verification. And finally, on the extension side, we have extensions for elliptic curve cryptography operations like ECDSA, pairing over BLS 12381 and BN 254, as well as hashes like Ketchak and SHA-2. Finally, I wanted to mention that on the roadmap, the first order item is to build towards a more production-ready release. So there's a lot of performance and optimization work, as well as, of course, security work. So we're trying to be careful with when we try to go to production initially, but we're targeting in the next few months.
I'm also curious about the developers. One of the things I like to do usually when I check a project is to see in GitHub, like who are the contributors and what are they working on. Can you describe how it looks like internally? Because there's like quite a big team already working on this project.
Yeah. So I would say the directions of development are, of course, the Rust toolchain side. We have a sort of new way of incorporating new precompiles or VM extensions into the Rust front end. So we have some engineers who are building that. Then on the circuit side, of course, there's the full RISC-V support, as well as the different extension chips for hashes and elliptic curve operations. And finally, on the proof system side, we owe a pretty big debt to Plonky 3, which is providing the Fry support. In terms of collaboration, we've been working with Scroll, and so one of our advisors, Max Skillett, on the design of OpenVM. Took a lot of inspiration from both their previous work and just very ongoing discussions on the design there. And in terms of the contribution model, we are looking to open up contribution to a greater set of contributors as we sort of grow the project. With the initial release and open sourcing last December, we brought on a few smaller contributors and hoping to grow that in the future.
What kind of contributors are you looking for? What skill set, for example?
Yeah. So one thing that we see an opportunity for with OpenVM is to onboard teams who want to use the core VM framework, but for sort of very different applications. So a couple areas that we're interested in are plugging in different backends into OpenVM. So we currently support a Fry backend with Plonky 3, but we have an abstraction layer that allows different parts of the system to use different proof system backends. So that's something we're pretty excited for to offer future proofing for developers. Another direction, which is kind of parallel, is to support mobile proving by customizing the backend a bit to reduce RAM memory usage, as well as potentially power consumption. In general, we feel like these are use cases where it's not necessarily a top priority for us, but may be really critical for applications that other developers are interested in building.
Focusing on the use cases, who will be the ideal user for the ZKVM, and how this user type will evolve over time?
Yeah, in general, we think that the ZK market is definitely growing over time as capabilities progress. I would say today, probably the largest user would be ZK rollups. Certainly, in terms of deployed applications, that's the broadest usage of ZK. And we do think OpenVM can really bring some new capabilities for rollup teams. Basically, because of the extensibility, those teams are able to add custom components that are verified efficiently in their rollup without having to fork an upstream repo or coordinate extremely tightly with a ZKVM team. But we are pretty excited about growing the market for ZK, and a couple emerging applications we're interested in are the general category of using ZK to bring the Web 2 data into the on-chain or Web3 context. There, I think one of the advantages of our modular design is that there's obviously a very heterogeneous there's a very heterogeneous set of cryptographic algorithms that are present in Web 2 data. And to really, bring that on chain, you really have to deal with the complexity there. And so we feel having a more modular design can really enable that.
Yeah, we found that in the Web 2, Web 2 has a lot of security that's already been built into it. And there are a lot of options out there. And so you really don't want to like reinvent the wheel or like have to customize every single part of it from scratch.
Can you explain this point, Jonathan? What do you mean Web2 already have a lot of security?
Yeah, just like in like the existing Web2 different kinds of protocols, like they always there's a bunch of different types of encryption used, like different algorithms, and then for security and also for optionality, like it's not just going to be like it's not always just like this one curve, and it's not always just ECDSA. It is quite varied in terms of the different types of like algorithms and like the different kinds of security considerations there. So it's really not just like if you have this one function, you're like good for Web 2.
I'm curious. I think ZK is a very high barrier niche sector for people to build. So I'm curious, with the introduction, like the frameworks like OpenVM, will it like lower the barrier, and will we see a boom or like more inflow of the developers in ZK, like something OP Stack, which lowers the barrier of building layer 2s?
Yeah, our perspective is that if you want to just build in ZK kind of as a specific vertical, the barrier will probably continue to be pretty high because it's a super technical area. But where we see OpenVM being helpful is to enable developers who don't necessarily consider themselves ZK developers to make use of the properties of ZK. I think there's obviously been a lot of activity in ZK over the last couple of years, but what we think has held back adoption is the combination of a lack of flexibility as well as a lack of performance, to be frank. And so what we're hoping to do is with OpenVM is to allow developers who don't necessarily care about ZK, but more about the trust guarantees that ZK can give to very flexibly perform pretty non-trivial operations in ZK for their application purposes, while still retaining the flexibility to tailor something for their needs if there is some particular operation that's holding them back performance-wise.
What does the developer experience look like? Are there something like they still have to bear in mind that probably like security or whatever they should pay attention to?
Yeah. So we offer a Rust front-end interface, so developers can write relatively ordinary Rust programs, and they can interface with our VM extensions through a standard Rust interface. So to, for example, use the extension for Ketchak, they really just need to import our custom Ketchak crate, which shares an interface with Ketchak crates they're already probably familiar with. That said, when a developer is making use of ZK, they do have to keep in mind what are the trust assumptions and properties they're getting and perhaps not getting. So both for computational integrity, that's important. I think that's very similar to more traditional blockchain engineering. And if they want to use ZK for privacy, then of course there's a whole world of pretty dangerous trust assumptions that they have to be careful about. So our perspective is that, hey, developers that want to use ZK as a tool need to keep in mind what they're doing, but what we want to solve for them is the technical details of really achieving those trust guarantees.
Sounds like it is inviting in some way. And by the way, disclaimer, I haven't tried yet myself OpenVM, but it is inviting in some way people to build more tools on top of OpenVM, before reaching the application layer. Might be the case. So would you say so?
Yeah, I think we would love for even external teams to build tooling on top of OpenVM, and we actually think that this is very similar to, for example, a database in the Web2 context. There are a lot of companies that build open source databases and then tooling on top to make it easier to use for users. So with OpenVM, we think of it much the same. So the reason that we wanted to make the base framework extremely flexible and modular is to enable certain extensions that might be more directed for specific use cases. And moreover, we decided to release under this more neutral GitHub organization to promote this spirit of collaboration among different teams. I think if OpenVM were in the Axiom repo or the Scroll repo, it obviously would be pretty challenging for another team to want to build on top of it or contribute to it in a very significant way.
Got it. Let's talk a bit about the architecture. And one unique feature of the design is something you call as no CPU. Can you explain what no CPU means?
Yeah, so in a traditional computing architecture, usually there is just one CPU or central processing unit, and like all the instructions do go through that central unit, and that's mostly because like there is something physical there, so like they are just physically adjacent, and you need for efficiency you need that central unit. And so usually when this translates into the ZK context, where you're using these polynomials to generate these different chips within a big circuit, what happens is that you just emulate this entire CPU into some big matrix of numbers, where it means every instruction, like in a program cycle, will be materialized within this big matrix. Usually something like, you can think that it's something like row by row, each row is some cycle. But yeah, what we call the no CPU design is that actually in ZK, because of the unique properties of these proof systems, mainly because there's some properties where you can use randomness, it actually means that there's no need from the like proof system level that all of these different instructions actually need to be in this one single location. And in fact, we found that for performance, it's actually better when basically the different instructions are just processed by the special chips that are optimized for them. And then, yeah, again, because of these proof system properties, the fact that the instructions are actually correctly chained together and like fit together correctly in the order of execution, that can all be constrained through what we call like virtual buses. But basically just meaning that the proof system has a way to do this using randomness that does not require everything to be in one place. And as mentioned, this gives both benefits in terms of the performance, but also it lends itself more to our modular design. And that's because in this central CPU design, if you want to add in some custom opcode and some special chip to support it, like the CPU in some way still needs to know about it. And that means like when you're just introducing this new opcode, you will need to then either change the CPU or just somehow be able to edit it in a way to get it to be compatible. But in this design, really every chip is equal. And so when you want, as long as you add this new chip to do some special operation and you have its interface match the interface that our architecture like requires, then it can just automatically fit into the rest of the system.
That's very cool. I wonder how it is this there's this notion of continuations that appear in other ZKVMs, and it seems like this modular design kind of like do you even need this like continuation in your case, or is it like replacing it? Continuation being kind of like being able to break your problem and then stitch it together, making it more parallelizable in a sense.
Yeah, we find it's a complementary concept and notion. Basically, the modular design is more at the circuit architecture level, which means it's how you can create some circuit with these different customizable chips to handle all of these instructions. But circuits are still, and by nature, a bounded entity. Meaning like it does still, it's something that you want to be able to run on like a single machine. And so it's going to have some limits on its size. Whereas continuations is what we implement on top of this architecture so that you can use the architecture to prove unbounded programs. So the usual assumption when you write a normal program is, well, if you just have a for loop that goes to 1 billion, it is just going to keep running until it gets to the end. And so there's no concept around like if something doesn't fit into the circuit there. And so the way to have that same property in ZK is that we have continuations, which is this idea that you take the entire program's execution and you break it up into what we call segments. And then each segment is then what is proved within a single circuit.
Got it. Staying with the design choices and again, putting it into the lens of how other ZKVMs are operating, specifically RISC-V ZKVMs, which is the more popular one. So I think that you guys also are classified as a RISC-V ZKVM, but if I understand correctly, there is something different here, right? So one thing I noted is that the connection is not immediate. Like you have this ISA that is more general purpose for VMs. You just chose to implement RISC-V using it, but you could have implemented like other stuff with it. Did I get it right? Can you share more about your ISA and this design choice?
Yeah, which also really shows you've studied our design quite carefully to be able to notice this point. Yeah, so it stems from an interesting realization we had, which is that in the ZK virtual machine context, like you don't need to make the same trade-offs that traditional hardware-based ISAs need to make, because they need to really think about like the exact how to make these things really match like some kind of physical thing. And then as a result, you can't have, you do need to just make a choice of architecture, very, very, very specific. And then that's the only one that you can support. Whereas we have a system with using our circuit architecture, we are able to support different kinds of like we're matching up with more traditional hardware architecture. We can support different kinds of ISAs within the same overall framework. So what that means is that we have some very general ISA framework that is in terms of like more ZK specific things, but you can fit in different kinds of other like things like RISC-V or more specific, more specialized instructions for example, native circuit recursion, and have them all live within the same overall ISA architecture. The reasoning for this was that when you want to do custom things, you may not want to use like one specific RISC-V architecture, but then also like there's no reason that in order to support this custom thing, you need to like reinvent or re-implement your entire VM architecture for that other specific purpose. So we arrived at this design partly just for our own internal uses, which is that to support like Rust, we have some of these instructions that can be transpiled from RISC-V. But on the other hand, we use the same architecture to do the Stark recursion, which uses a more just not RISC-V compatible instructions in terms of native field elements.
The ISA is actually included in the modularity of the system. So what that means is that developers are able to, who really want to, are able to define their own opcodes that they would like to mix and match with the opcodes that we've implemented. And they can have those opcodes interoperate with, for example, RISC-V opcodes or native recursion opcodes in the same set of shared memory spaces. So we have certain memory spaces which are designated to be RISC-V format, meaning that each field element contains a byte, and 4 bytes consists of a RISC-V word. Whereas there are other memory spaces where each field element is a full field element, and those are intended for recursion. And so in principle, at least, it would be possible for a developer who wants to implement WebAssembly in this framework to have that running totally in parallel with the existing RISC-V or native recursion frameworks.
I have to admit, this is brilliant. Yeah, I can also add RISC-V extensions, right, as much as I want, and so on. So yeah, it looks like a very powerful feature, and this is great. I guess that the last thing I wanted to ask on the design space is, what inspiration did you take from other ZKVMs, right? You are not the first one in the ZKVM space. So what learnings and what inspiration you got here?
Yeah, we definitely studied quite a few of the existing designs. I would say we took a few things from each of them. From RISC-0, which I think was the first RISC-V ZKVM, we're actually using a fork of their Rust toolchain. So they managed to get their Rust toolchain merged into the official Rust repository, which we think was extremely impressive. So we do handle certain things like syscalls slightly differently from them, as well as the way we handle extensions. But yeah, we drew a lot of inspiration from their toolchain code. A lot of the way that we handled cross-chip communication is drawn from Velita. Velita, I think, introduced a really nice abstraction around using a logup argument in a way that they call interactions, which we use pretty heavily in the lookup arguments and similar communication. And then we also, obviously looked at SP1. We took some inspiration from the way they handle basically, I think they call it, our handling of extensions is somewhat related to the way they handle, I think they call it precompiles, but I think the underlying mechanism is still a little bit different. And then finally, for overall context, we did study Cairo and Maiden just to understand kind of the foundations of how ZKVMs work. But I don't think that we took anything very directly from those.
Got it. Thank you. So also wanted to ask about the prover technology itself, about Starks, field choices, anything in the ZK stack that may change in the future. I mean, right now you are using Stark-based provers. Is there any other proving systems you are looking into?
Yeah, so I think one thing is we use the term Stark very, very loosely, or at least we think of it that way. And so, yeah, overall on our Stark backend system, the goal is to make it modular and also to make it as future-proof as possible. So I think we have been making changes to improve the interface so that even if or while for example, the Rust and the opcode level stays the same, if we want to change it to a new new proof system, then we can do that purely at the backend level without having to immediately rewrite all of the circuits. And yeah, so I think we think about Stark backend is more as being just this modular layer where different kinds of proof systems can plug in. Yeah, I guess that being said, we do for Stark, we do feel like Stark means things that are hash based and likely smaller fields, like 32-bit or less. But we are very interested in not just the current Stark implementation, but yeah, trying out new ones as they come out.
Yeah, I've seen that you also made, Jonathan, some contributions to Plonky 3. So I guess, is your Stark, is it currently implemented, going to be different, or is different from the canonical Starks in any significant ways?
I think more that it's at this slightly higher layer where we use Plonky 3 heavily, but Plonky 3 is operating more at this pure like polynomial commitment scheme level, but it doesn't, for example, do the things like log up or handle if you have multiple chips, how they should be proved together, and to handle like inter-chip communications and stuff like that. So right now our Stark backend is mostly around how to build that layer on top, and in a way where you don't have to redo it each time if you want to change out some of the parts, for example, in terms of polynomial commitments.
And maybe to add one thing about our general philosophy on the proof system backend, like one development goal for OpenVM is to enable developers at all levels to try to swap out the level below and really see whether there's a performance improvement without having to rebuild significant parts of the system. So for developers who are writing in Rust and want to get their Rust code proven in a ZKVM, our goal is to really maintain a stable interface that can have the underlying proof system swapped in and out without developers needing to change really anything about their code. For developers who are more interested at the ZKVM level, one objective of our system is to allow incremental shifts between proof systems. What that means is that although we're currently using Fry, we're interested in, for example, testing out a sum check or GKR-based method on parts of the system without having to migrate the entire system at once. And our feeling is this sort of incremental nature can be more appealing for developers who want to experiment with different things without necessarily committing all the way initially.
Got it. Great. Did you have a chance to compare performance against other ZKVMs already? Is there like some standardized way to make it apples to apples at all?
Yeah, it's always been a controversial topic in the community. We haven't tried too seriously, but we will in the coming months. To give a sense of our philosophy here, right now we are really running proving on CPUs. And actually that makes it a little difficult to really make an honest comparison because our understanding of some of the other teams are heavily optimized for GPU proving. And obviously we'd have to be significantly better to be competitive on CPU. So I would say we've stayed away from trying to do competitive benchmarking. Or in our announcement post, we explicitly did not want to have, a graph where we have a very small number and everyone else has a very large number. But our hope is that actually there are some efforts coming out in the community by more neutral third parties to do benchmarking. I think the Ethereum Foundation is driving an effort to prove Ethereum mainnet blocks. We think that's a pretty representative benchmark. And yeah, we look forward to sort of participating in that.
So actually, I want to learn more about the collaboration. So you mentioned, for example, OpenVM is collaborating with Scroll, but Scroll has its Sino, the ZKVM. So how does Sino work with OpenVM?
Yeah, actually, the origin of the collaboration started in kind of the early development phases. Basically, at the time, Scroll had been working on what eventually became Sino, and we were thinking about how to just exploring the space of ZKVMs. And so we started, just discussing ZK research ideas and how the different systems should be architected. And at some point, we really saw a bit of convergence in the architecture, and so decided to sort of release OpenVM together, sort of as something that could potentially go to production faster than Sino. And so with Sino, Scroll's continuing some explorations on the GKR side, but we see a future where actually the Sino backend is plugged into the OpenVM front end, which could basically dramatically accelerate some of the development while potentially giving some performance benefit to users of OpenVM. So a bit more generally, our philosophy is that we're pretty agnostic on the backend side. We think that we want to give the best, development environment for developers, and part of that is their developer experience, but the other part is always providing them the fastest backend on the market. And so to do that, we think collaborating with different teams who are working on, different types of proof systems, different backend approaches is critical.
Got it. Then from a business perspective, how would OpenVM different from other ZKVMs?
Yeah, I would say, and I don't want to speak for the other teams too much, but the general approach in the market for ZKVMs is to try to vertically integrate around a specific ZKVM design. Our philosophy is, I think, almost the opposite of that, where we explicitly want OpenVM to be kind of a neutral place where different teams can collaborate. And on our side, as a business, we will be building some first-party blockchain products on top of OpenVM, as well as offering a hosted platform and services to support teams using OpenVM. But our perspective is much more that we view OpenVM as a way to uncover new use cases for ZK and to support them, rather than trying to lock users of OpenVM into our proving or a marketplace that we own. Yeah, we'll have more coming out about this in the next couple months, but pretty broadly, we're interested in kind of new rollup designs, which are uniquely enabled by having very tight coupling between the ZK stack and how the rollup actually works. And in addition, we have some internal work in progress on how to really radically use these VM extension properties of OpenVM to basically ZKify a much broader scope of software. So sorry to be a little bit vague there, but you'll see some announcements from us in the next couple months.
Okay, sounds exciting. Omar, you have some follow-up?
I just wanted to clarify, so this is not going to be a network, like not a proven network or token or something like that?
Yeah, no current plans for any sort of network or token. Right now, we're really focused on really establishing OpenVM as a piece of open source software. And for us, that means both the licensing, but more importantly, the contributor model and having a pretty robust scope of contributors. We ultimately feel for a developer using a ZKVM, the most existential risk is that the developer really needs to trust the team developing the ZKVM. And we hope that if we can attract a diverse enough pool of contributors, we can remove that risk from developers' consideration set.
And one thing I'm also curious, because you also mentioned, for example, you will also join like ETH proofs to prove Ethereum blocks and then to see like the actual performance. So I'm curious, how do you envision this trend? Like, do you think like in the end there will be a winner takes all, or it will end up like everyone has pretty similar performance?
Yeah, it's a good question. I do think that every player will be pushing performance over the next year. Our sense is that the value of performance does plateau at some point. I think certainly we're not close today, but we are in 2025 able to see a place where performance is not necessarily the limiting factor for developers anymore. And once that happens, we think that customization, the ability to very flexibly address use cases that are maybe even much larger than verifying Ethereum mainnet blocks, those will be important. And so when we think about the longer term architecture and development of OpenVM, we want to make sure that we're providing a future-proof solution for developers. And we kind of, although we view, proving blockchain execution as an important use case, we don't want to overfit to it. And like our hope is that developers who will build on or using OpenVM can discover like many different new application areas and try to tailor, their usage for those areas.
This is very insightful take.
Yeah, before that, I wanted to touch on one last topic, but feel free to tell me if you want to skip it, because I was interested to learn more about the relationship or this kind of evolution that you guys made from coprocessors into OpenVM. What were the learnings from that process? Also, just in general, what's going on now with the Axiom coprocessor technology and products?
Yeah, it's a great question. I would say the origins of OpenVM really were in our frustrations as ZK developers building the initial versions of the Axiom coprocessor. We repeatedly heard from potential customers that what we had built was not flexible enough. It would frequently be very, very close to what developers wanted, but with a slight tweak. And we were very frustrated that it was difficult for us to create even these very small changes to the product. And so the origin of that was that at the time that we set out to build the coprocessor, the main way to build anything in ZK was to use custom circuits. And so we went very deep in building custom circuits for reading from Ethereum data structures, and even keeping up with hard forks on the L1 started becoming a problem because those data structures would change and we would have to modify circuits to keep up. So it gave us a lot of conviction that the ZKVM development model was kind of going to be the long-term, more viable one. And so when we thought about how to adopt that, the coprocessor use case was actually one which drove us to really feel the need for customization. So initially we thought about trying to build a better version of the Axiom coprocessor with a ZKVM model, whether an existing ZKVM or one we create ourselves. And so we felt when considering adopting an existing ZKVM that there's quite a bit of developer lock-in and a lack of some aspects of flexibility, which we felt would be later necessary for some product features. So then we went on this pretty big exploration of, hey, maybe we don't need to build a full ZKVM, just some very minimal one for our needs. That turned out to somehow not be enough. And then we realized by that point that we had built enough of OpenVM that it was kind of everything but a RISC-V ZKVM. So at that point, we decided, hey, we should really get to the endpoint, add RISC-V, and get to something near approaching the release we had last year. So maybe one Easter egg here is that probably unlike every other ZKVM, the RISC-V component was the last component that we added in. So I think a lot of the development might look a little bit strange from that perspective. In terms of the coprocessor, we did deprecate the Axiom coprocessor as of the OpenVM release. And it's an area that we're looking into coming back to in the future, but we feel that actually it's better to first get OpenVM to really a state-of-the-art state where we think that it's going to accelerate our development the most.
Yeah, I think this leads us to the last question, which we ask all of our guests, and it is to name a project you are bullish about, any project.
Yeah, I guess I can go first. I don't know. Well, it's just a GitHub org, but the R55ETH project. So they are exploring how to be able to have Rust smart contracts coexist with EVM smart contracts in the same execution environment. It's still very experimental, but I think the ideas there are really interesting. And yeah, it's now that from what we're building, it's like kind of got a mix of everything you could want, like RISC-V, Rust, all the VM stuff, and then yeah, of course, EVM.
Yeah, on my side, I would say this is maybe a little bit boring, but one thing I'm really excited for in 2025 is the continued growth of stablecoin adoption. And so to name something a bit more specific, I am kind of excited for the scaling of Circle CCIP. I think it just can offer the theoretically best bridging performance. And I'm excited for more users to kind of discover how to use this, whether directly or through more user-facing wrappers like Dymo Pay, which is offering like a truly great payment experience on top of CCIP.
Amazing. Thank you for the answers. And I think it is our time to wrap up. So Jonathan, thank you again for joining us today, sharing information about OpenVM and your journey and your plans for the future. I think it was insightful and I enjoyed it a lot. So yeah, for those interested to learn more, we've added some links in the show notes. So thank you, everyone. Thank you, Queenie.
Thank you. Thank you, guys. I'm excited for OpenVM in 2025.
Yeah.
Thanks so much for having us on.
Thanks a lot.
It was a pleasure.